Hello to everybody. This is the third lecture on this series of lectures on matrix algebra. In this lecture we will discuss about linear independence and a rank of a matrix, and we will discuss about the conditions on invertibility of a matrix. Okay, let's start defining what is a linear combination of vectors. If we have linear combination is a definition. We have that a linear combination for n vectors for then v1, v2, vn that are vectors, v1, v2, vn are vectors that are, for example, n by 1, n by 1, n by 1. If we can write the sum of alpha I b I, where alpha I is a scalar, a real number, then, for example, if we have v1 that is equal to, I don't know, 1, 2, 3, and v2 that is equal to minus 1, 0, 1, then a linear combination of these two vectors are like if alpha 1 is equal to 1 and alpha 2 is equal to 2, is alpha 1 v1 plus alpha 2 v2. Then is like 1 by 1, 2, 3 plus 2 times minus 1, 0, 1. And this is 1, 2, 3 plus minus 2, 0, 2, that is equal to minus 1, 2, 5. This is a linear combination of v1 and v2. Then we can choose, some constants or some scalars, alpha 1 and alpha 2, that combine v1 and v2. Okay. Now we can define what is a linearly dependent what is a linearly dependent vectors. We say that v1, vn, that are n vectors, are linearly dependent if there exists a linear combination such that the zero vector is sum of alpha I. For some alpha E that are different from 0. Then if we find some linear combination with some of these scalars that are different from 0, such that we get a zero vector, then this 0 we can see like 0, 0, 0, 0. And then we can say that these n vectors are linearly dependent. But what we are interested in are the linearly independent vectors. independent. And we define V1, V2, Vn linearly independent. If we get the zero vector as a linear combination of the VI's, implies what? That the alpha I is equal to 0 for OE. An example of linearly independent vectors can be this one. I don't know. 1, 0, 0. 0, 1, 0. And 0, 0, 1. V1, V2, V3. If we try to do this one, alpha V1, alpha 1 V1 plus alpha 2 V2 plus alpha 3 V3, then the only way that we can get a zero vector, then a 0, 0, 0, is when contemporaneously we have alpha 1 that is equal to alpha 2 that is equal to alpha 3 that is equal to 0. Because this one leads the third component, this one leads the second component, this leads the first component. And then the only way that when we sum up these vectors by some constants in order to get a zero vector is when alpha 1, alpha 2, and alpha 3 are equal to 0. And this is the concept of linear independence. And it's very important because with linear independence, then we can define what is a rank of a matrix. Then if A is a matrix, let's suppose that is a m by n for now. Then we say that the is rank, the rank of a matrix, that we can say rank A, is the maximum number of linearly independent columns, vectors in the matrix. For example, if A is something like that, 1, 0, 0, 0, 1, 0, 0, 0, 1, we have shown before that these vectors are linearly independent. These V1, V2, V3 are linearly independent. And then the rank of A is equal to 3, because 3 is the maximum number of linearly independent columns, vectors, in the matrix A. And then this one is the maximum number of linear independent vectors that we can have in this matrix, because we cannot have more vectors. The A is defined like a 3 by 3 matrix, and then we can have, you know, not more than 3 linear independent vectors. Okay, and there is a rule that if A is a m by n, then the rank of A is surely less than the minimum of m and n. Then, you know, if you have, you know, for example, a matrix like that, 1, 2, 3, 2, 1, 3. Okay, this matrix is A is a 2 by 3, and then the rank is for sure less of 2. then rank of A is less than 2. Okay, and this concept of rank of a matrix is linked with the invertibility of a matrix, because we can say that a matrix A, that is a n by n, is invertible if the rank of A is equal to n, or we say that is a full rank matrix. Okay, and this is a fact that we know, we want to know, because for example, in certain case we need to have that, for example, we want to invert a matrix that is done like that. This is m by 1, this is m by k, this is a k by 1, and this is m by 1. This is a k by k. And then in a certain point, we want to invert this matrix. Okay, I think that you know what is what is the inversion of a matrix. Is defined. You can find, for example, in some books what is an inverse of a matrix. But by the way, this is invertible if and only if x transpose x, the rank of x transpose x, is equal to k, because usually this k is smaller than n if we want to solve this, this problem. And yes, and this is what we need to know for the invertibility, because for example, this there is one assumption in the regression model that says, okay, we want that the rank of x is equal to k. Okay, there is an implication that if this is true, then the rank of x transpose x is equal to k, and this means that we can get this one. This exists. Yes, I want to recall that the invertibility is referred to matrices that are m by n. In this case is k by k, okay, square matrices. And yes, and then there is a link between invertibility and then an inverse of our square matrix and the rank. You need to remember that the rank of this matrix has to be full rank, in the sense that if the matrix is m by n, then the rank of the matrix is n. And I think that with this one, with this remark, we have finished for this lecture. And then I say thanks and see you for the next lecture.